Okay, everybody. I'm going to try a new software here in which I can do some examples and then I can post them via video. This will help, especially when we run out of time and I can't get to examples, which sometimes happens because I'd like to answer as many questions as possible in class, but I still want to get to those examples. So if this works out well, I'll be able to do that. And also, I will be traveling sometimes. I only have 1 week planned this semester, but if that's the case, I'll be able to do the lecture through video. So this will be my first attempt at using this, so bear with me if there's any technological issues. But on lecture 2, example 2, we weren't able to get to that in class, so I'm going to go ahead and do this example so it gives you a little more practice. Okay, so in this example here, you can see that we're given a vector field. A is equal to rho cosine of phi a rho times rho z squared sine of phi a z. We want to transform A into Cartesian coordinates and want to calculate its magnitude at the point 3, -4, 0. So we did a similar problem like this in spherical coordinates the other day. But this one's in cylindrical coordinates, so it gives us some more practice. Okay, so what we're going to do first is we are going to write the vector field. Okay, so A is equal to rho cosine of phi a rho plus rho z squared sine of phi az, right? So we want to transform this into Cartesian coordinates. So what we have to do is first we have to transform the variables and then we have to transform the vectors, okay? So we can see that we have rho cosine of phi z squared sine of phi. Well, in Cartesian coordinates and cylindrical coordinates, z is the same thing. Z is the same thing, and so is the unit vector az. So we don't have to do anything with the z, but we do have to transform the rhos and the cosine of phi. Okay? Now, we should note that we can make the transformation by saying that rho is equal to x squared plus y squared, right? And then as far as phi, we can take the inverse trigonometric form to find out what phi is, but if we have a cosine of phi or a sine of phi, we can use that as well. Well, recall that cosine of phi was equal to the opposite, which is x over the hypotenuse, which is x squared plus y squared, right? But you should also note here that hypotenuse x squared plus y squared is equal to rho, right? So while that might not be completely intuitive, I'll show you that x is equal to rho cosine of phi, and that's exactly what we have in this term right here, right? Likewise, sine of phi is equal to y over x squared plus y squared square root, right? And that's basically equal to y over rho. So y is equal to rho sine of phi, okay? So you can see here as we have basically x here, right? Erase that. We have x here, and we have rho sine of phi, so we have y here, right? So immediately we can say that A is equal to x times a rho plus y z squared az. Okay? Now, hold on 1 second, I just want to see if I can, well, that's okay. So we have a vector here, but the problem with the vector is that we have this unit vector here a row which is still in cylindrical coordinates, right? So what we'll do is we say we need to get that vector into Cartesian coordinate vectors, right? But we have a transformation, and we know from our equation that a row is equal to cosine of phi ax plus sine of phi ay, right? And we derived that in class the other day, and that is now can just be used since we derived it. So all we have to do is substitute a row in over here in our vector equation, and what we have is a is equal to x, and I'm going to substitute row in there, or a row in there, and I have cosine of phi ax plus sine of phi ay, right? And then we have plus y z squared az. Okay, so we're getting a little further, but the problem here still remains that we still have cosine of phi and sine of phi. Okay, so allow me to add a new page here. Okay, and I'll take it from there, and I'll say that a is equal to, jump back here, a is equal to x cosine of phi ax plus x sine of phi ay plus y z squared az. Okay, so now we're one step closer. We have basically everything today that we need, except the only difference is we have these phi angles in here, right? But we can go back and we say, oh, well, we already know that cosine of phi is equal to x divided by x squared plus y squared square root, right? And we know that sine of phi is equal to y divided by x squared plus y squared square root, right? So now we can simply substitute those two things in, and we have our value here. So now we have, substituting x divided by x squared plus y squared square root for cosine of phi, we're going to have x squared divided by x squared plus y squared square root multiplied by the ax vector. And then when we put sine of phi in here, we're going to have xy divided by x squared plus y squared square root. Let me erase that y. Multiplied by the ay vector, and then we're going to have y z squared az. Okay? And that is our vector now transformed into Cartesian coordinates. Okay? So the next part of the problem said, well, we're going to take that and we're going to find out what the magnitude of that vector is at a specific point. Okay? So that point is, let's see. Again, you just have to bear with me here as I learn this new technology a little better. I think we go here. Okay, so we went to point 3, negative 4, 0. Okay? So let's go back here. So at the point 3, negative 4, 0. Okay? So if you see 3, negative 4, 0, x squared plus y squared square root at that point is going to be 3 squared plus 4 squared square root, which is going to give us 5, right? So basically what we're going to have is x squared, so 3 squared, 9 divided by 5, ax. Okay? And then on the other side over here, we're going to have 3 times 4, which is negative 12 divided by 5, right? Minus 12 fifths AY, right? And then we're going to have y, which is equal to negative 4 times z at this point, which is 0, so we have no AZ component, okay? So that's evaluating the vector at this point. I'm not going to do the magnitude. Everyone, I think, knows what to do at this point. You would simply just square the AX term and square the AY term, right? So magnitude of A would be equal to the AX term squared plus the AY term squared, square root, right? So the magnitude of A, I'll just write the formula, is going to be equal to 9/5 squared plus 12/5 squared square root, right? And that would produce the answer that you need. Okay? So everyone, I hope that this video worked out well for you. It's the first one, so it's a rough cut, and I'll get better at them as I go along, but I think that we'll get a lot of benefit out of using this, and I'll be able to add a lot of additional support to the course. Okay, thank you.